Okay, everybody, I just want to show you something simple here about efficiency, or not the efficiency, but the mechanical advantage. So the mechanical advantage of this situation here would be the distance of the input divided by the distance of the output. And as you can see that the guy is going to be running up the stairs, the distance of the input here is going to be 4 meters. And ultimately, all he wants to do is get 2 meters higher. So that's his output distance. So the mechanical advantage of these stairs is 2. And you can see the units cancel out. Okay, here's another situation here. So this is an inclined plane with a fulcrum here. You can see that the lever arm here, where we're putting our input force, is much longer than where the output force is coming into. So we're going to do more than one thing with this to kind of explain how these things go. But if you want to do the mechanical advantage, then, and this is the ideal mechanical advantage, it'd be the input distance divided by the input or the output distance. And so we can talk about the lever arms being, distance from the fulcrum to the input force, distance from the fulcrum to the output force, could be 3 to 1. So the mechanical advantage is 3 in a perfect, non-frictionless world. So with that situation, you can say, well, geez, if I'm going to be lifting 60 newtons and I have a 3 to 1 mechanical advantage, then that means that I must be putting in how many newtons of force? Well, what goes into 63 times then would be 20, right? So I put in 20 newtons of force to lift a 60 newton weight object like that if I have a mechanical advantage of 3. Now in reality, I'm going to have to put in more than 20 newtons because this is ideal mechanical advantage, and actual mechanical advantage is going to include friction. Now what's interesting about this though is with levers is, you can get your mechanical advantage from the distance to the fulcrum, but because of the force distance trade-off that we've talked about, what you do is you have the same ratio of more distance that you have to put in with the less force here. So this force that I'm putting in is three times less than this force that I'm getting out of it, but I still have to have the same amount of total work. So if I'm putting in 3 times less force, that means I have to do 3 times less distance, or 3 times more distance, I'm sorry. So in this case, if I put this force here of 20 newtons, and let's just say that this is 1.5 meters from here to here, so 20 times 1.5, my total work then is going to be 30 joules, right? Well, in order to get 30 joules out of this, it's still force times distance for work. If my force is 60, then my distance to get 30 joules is going to have to be 0.5, which makes sense that this is only 0.5 meters that I'm moving this bigger force with. Okay, so hopefully that clears up some of the ideas about the force distance trade-off and mechanical advantage.